Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about triangles and circles. In particular, we're going to be talking about situations where we draw them together, inside one another, outside one another, different relationships, and how they fit together that way here. So let's get started with a couple of definitions to start here. Our first definition is that of circumscribed. So circumscribed means to draw outside or around another shape there. So I'm going to do this a little bit backwards here, but if we kind of have a circle, then what we could be drawing is, if I have a square, we could draw the square inside the circle, or how we'll typically describe this is that this circle is circumscribed around the square. So we have our circle that is circumscribed around that square there. Now, of course, if we have this idea of outside, we can talk about inside as well. So inscribe means then to draw inside. So I could draw a circle inside this square as well, and that would be the inscribed circle there. Of course, these things are relative, right? The brown square is circumscribed about the green circle. You could say that, but typically you talk about a shape like a square, or today, of course, a triangle, and then we talk relative to that. So circumscribe is outside of that triangle, inscribe would be inside of that triangle, and we go from there. I always like looking at the words to help with vocabulary there a little bit too. So we have this inscribe inside of the square. So we have inside, and we have the in portion of the word there too. We have around outside, right? This is then circum here. So for example, you have, right, circumference or circumnavigate, right? These are words that kind of give us this idea of around or outside things there too. And then of course we have scribe here for the drawing. So you might usually associate this with writing, but writing is kind of the same as drawing. You can also think of the word scribble, right? Scribe is someone who wrote things down or drew things in ancient times. So this is just nice ways to kind of remember these words and where they come from here as well. Like I mentioned, we're going to be talking about triangles particular today. Let's look at some examples there and some of our kind of facts as well. So this is a fact. A circle can always be inscribed inside a triangle there. Right, this isn't necessarily obvious, right? It's pretty easy to kind of draw the picture and stuff there. But this is a fact that we have. And this circle is called the incircle. The radius is the in radius. It's typically called a little r when we're talking about this in radius there. Now, when we're looking at this picture too, let me kind of just describe this a little bit more, right? When we say inscribed inside a triangle, what we mean is that the circle is tangent to the three sides of the triangle. So the circle is simultaneously tangent with these three sides, right? So we're going to kind of do this forward, assuming it exists, and draw some properties from here. So we have, of course, our three little radii here, the in radii in this case. Now, in a lot of these diagrams, this is going to be very similar to the diagram we draw for outside of the circle too. We want to be looking at the radii and to the points on the side of the triangle, but we also want to consider how this looks when we connect it to the vertices of the triangle as well. So in this case, we have three right triangles here. Now, depending on how you want to think about this or the properties you want to look at, we have a bunch of actually pairs of congruent triangles. So So let me kind of highlight it this way, right? If we look at this right triangle here, that right triangle is going to be congruent to this right triangle. They have the same hypotenuse and one shared side there. Right, so actually then, right, we actually have kind of two common distances in that case. So let me kind of just draw these in there as sides. The important thing I want to kind of point out here is that these two sides are the same length in that case. And we can do this same argument for the other pairs here as well. So we have these two right triangles are congruent there too. So these two portions, these two lengths of these right triangles are the same. And then we have the same thing on the top as well. This pair is congruent too. And therefore we have these sides that are congruent there as well. So those sides are the same length in that case too. Now let me just clean up that picture without the highlighting, and we can see, however, we're left with these kind of pairs of triangles that are all the same in this case. Now, this actually gives us a little bit more, and this is going to be the punchline on the next slide as well. Because these pairs of triangles are congruent, we actually have that these angles are the same, right? They're two congruent triangles, so those two triangles have two angles there of alpha. These angles here are some different angle, let me call those beta. And then at the top, of course, we have congruent angles, maybe gamma in this case there. So we have these 6 triangles. They divide up into 2 pairs of congruent triangles, and we have these equal angles in that scenario. So what is this actually telling us? This is actually telling us that we have what are called angle bisectors. So remember, an angle bisector is a line that divides an angle into 2 equal pieces there. So the center of this circle, right, if we look at the center of this circle then here, this incircle, called the incenter. I know this is a very creative name based on the other ones there, but this is the intersection of the 3 angle bisectors of the triangle there. So we kind of did this in reverse, right? I showed you the circle, the center of the circle. I connected that circle. We formed our triangles and stuff there. But this gives you an idea of how you could prove that this circle exists, this in-center exists. You start looking not at the circle first, but you start with the angle bisectors. So if you do kind of the whole thing we just did in reverse, start with the triangle, then look at the angle bisectors and look at the properties you have from there. That's kind of the real way you would prove some of these things, or prove the existence of this in-center and therefore the incircles, stuff like that too. But for practical purposes, for knowledge at the beginning at least, it's good enough to kind of know all of these relationships. So this is a very important picture for the angle bisectors, the incircle. We have these 6 triangles and their relationships that way for the incircle in this case. Let's shift gears then to the outside one. And again, this is possible. So a circle can always be circumscribed around a triangle or outside of the triangle there. In particular, again, this means now it contains the 3 vertices. So this circle is called the circumcircle. It has a radius called the circumradius, r in this case. So we have these, again, radii to draw in first. Right, just a little bit about the notation. Notice that the incircle was a little r. The circumcircle is typically done with a big R in this case. So we have kind of the radius here of these 3 triangles, or sorry, these inside the triangles there, connecting to the 3 vertices that are on our circle in this case. Now, let's think about dividing this into the 6 triangles like we did before. This one's not as obvious or not as kind of clear what to do, right? We had the radii before, we connected them to the vertices. That's a pretty natural thing to do here. In this case, however, let's divide this into 6 triangles by drawing the altitudes. So I want to draw, again, we'll end up with 6 right triangles, but something a little bit different happens here. So I'm going to draw the 3 altitudes for these triangles there. And again, for a second, let me highlight these in pairs. Now, right, I drew altitudes of 3 triangles. Let's consider the 3 triangles we have in this case, right? So we have our 3 triangles there created by the radii, and I want to look at those 3 triangles here as well. Now, again, these pairs of right triangles we create share the hypotenuse and they share the height. They share one side in this case. So again, these 3 pairs are congruent in this case. So again, actually we have this is a midpoint, right? We have congruent triangles, so we have a midpoint on each of the sides here. And you could also think about this as a circle property, right? When you have a circle and you have a radius and a chord, if that radius is perpendicular, or if a portion of that radius is perpendicular, we have a bisector. It cuts it in half in this case. So again, let me delete my highlighting there and kind of leave the punchline of stuff where we have these 6 triangles again. We have different pairs, but still we have congruent pairs of right triangles. And now that means these altitudes to the 3 sides of the triangle divide at the midpoint. We have 3 midpoints in this case there. Now, if you followed the pattern of the previous example, the incircle, you probably can guess where we're kind of going next. We can kind of think about where this center comes from, right? The center is called the circumcenter. So let's look at this the same way we did before. This is the center of our kind of circle in this case. It's this circumcenter here, and it is the intersection of the 3 perpendicular bisectors. Right, so if you start with a triangle, again, we kind of did it in reverse here in this video, but if you just start with the triangle, if you want to find the center and try to prove these properties there, you can start by looking at the perpendicular bisectors of each of the sides, right? So we have our perpendicular bisectors of each side of the triangle, and they all meet at this circumcenter. That is a fact you would need to prove and stuff like that. But that gives us then our pairs of congruent triangles, and that's where this consistent radius comes from. That center point is the same distance from each of the 3 vertices in this case there. And there's a lot more you can do with these centers of triangles, right? We have the incenter, we have the circumcenter here as well. There's actually more from kind of different intersections or with different properties that you can look at and study there as well. One note here, we're going to see a slight example of close to this in a second. The circumcenter doesn't need to be inside the circle there. For example, right, we could have, of course, 2 different triangles that have the same circumcenter. For example here, what if I drew this very obtuse triangle at the bottom, right? This triangle here has the same exact circumcenter. And so you can think about, again, these perpendicular bisectors and stuff. That still works. The picture is a little bit more complicated. You need to be a little bit careful with that picture. But the same type of idea goes there as well. So as a kind of follow-up to this, you could look at that and see what happens if we have this obtuse triangle and the circumcircle in that case. But let's look at one of our simple triangles, one of our famous triangles. And let's say we have a 30, 60, 90 triangle. We have some circumradius, we know that exists. We draw a circle around it, that gets the circumradius. And we have the in radius r, and we want to look at the ratio of big R to little r in this case. So we have a special scenario here where we have a 30, 60, 90 triangle. Now there's a couple of ways you could go about looking at this. One way would be with angles in a circle. You could also think about our perpendicular bisectors here too, right? If you think about what happens if you draw perpendicular bisectors in a right triangle, right? You're going to kind of get this rectangle, and it's actually going to give you a point on the hypotenuse, right? If you think about angles in a circle as well, this angle of 90 degrees means we have a 180-degree arc, meaning that our hypotenuse is actually the diameter of the circle. So the first thing we want to note here that's actually pretty nice in this case is if we have the circumcenter here drawn, actually the hypotenuse of this triangle is twice the circumradius in this case. So 2 times the circumradius is the diameter here. That's a nice property that's always true in a 90-degree triangle, in a right triangle there. So the 30, 60, 90, the 30 and 60 don't matter for this, the circumradius being the diameter, but as long as you have a right angle, that is going to be true. Now, we want to look at the in radius in this scenario too. Now, before I draw that, I want to point out that our final question here is what is the ratio of big R to little r in this case? And I want to just remind us that in a lot of these geometry questions where we have similar shapes, right? We can make things bigger, shrink them and stuff. In those cases, especially if you're looking for a ratio, notice nothing is given to us about the lengths of the 30, 60, 90 triangle. Of course, we know what ratio those lengths are in, but we don't know the exact information there. Right? We can then just assume a nice distance for the in radius r. So this, let's just assume that it is 1, right? That makes our life a lot easier in this case. You can double check that, of course, if you make it something different than 1, it doesn't actually affect our final ratio, because that kind of value will cancel out anyway there too. Okay, so we have our normal radii here now, except we have a nice thing that's happening where these are all 1. Now, before we do anything further even, I want to notice another nice property that we have here. In this lower right portion, we have actually a square. So the first thing we want to notice here is that we actually have a square in this corner. So this corner gives us a square in that case. So we have a square because we had this right triangle. We have 2 perpendicular lines. So we have to have a square in that case. Now, I'm not going to draw all of our dividing this into 6 triangles stuff here, but I do want to draw one in particular. In particular, the one that works nicely is the 60-degree angle. So if I cut this 60-degree angle, remember the in center comes from the angle bisector. So if we cut this angle there, right, either if you remember the bisector idea or just from these congruent triangles again, we have 2 30-degree angles in that case. So that itself is a 30, 60, 90 triangle. So we divide that region into 2 30, 60, 90 triangles, meaning we have some nice information there. In particular, remember our ratio for any 30, 60, 90 triangle, right? The ratio of sides in any 30, 60, 90 triangle is 1 to square root of 3 to 2. So that tells us, for example, this side is square root of 3. That is, right, the shortest side times square root of 3. And then the hypotenuse is the shortest side times 2 in that scenario. So we have our square root of 3 and we have our 2 in that case there. Now, how is this helpful? How does this actually kind of get us very close to finishing the problem from here? Right now, if we look at the original 30, 60, 90 triangle, right? If we look at our big triangle that we were starting with in this case, what do we know about that triangle, right? Well, what do we know about the short side in that triangle? The shortest side is, of course, across from the 30-degree angle, and that short side we've now calculated is 1 plus square root of 3. Now, what do we know about the hypotenuse, or the longest side, right? Well, first of all, we know that this is 2r in this case, but we also know that it is 2 times the short side. It's also 2 times 1 plus square root of 3 in that case there. But now we're basically done, right? Now we're done with the problem from here, because we know now the radius. We know that these 2's cancel in this case. So we actually have that our radius here is equal to, well, first of all, if we're assuming little r is 1, right, this is actually equal to the big radius divided by the little radius there. And that's just equal to, after we cancel out the 2's, 1 plus square root of 3. So that's where we kind of come up with this answer then there, right? When you're doing these ratios, take advantage of the assumptions you can make for the problem. And here our ratio is the same as our circumradius if the in radius is 1. And we have 1 plus square root of 3, 1 plus root 3 in this case. That'll do it for this video. Thank you guys for watching. If you enjoyed the video, please hit the like and subscribe below. It really helps out. Check back each Thursday for a new math tidbit in 2021. If you're just finding these, there's a whole archive now. I've been doing these the whole year, so you can take a look at a lot of those math tidbits that we've already done in the past as well. And if you're looking for other resources, please check out ZIML.areteem.org. There's some good daily practice there, other archives of math competitions, monthly contests, a lot of great things you can do on that site and by joining that Zoom International Math League community as well. Goodbye.